This time, I'm going to talk about how to perform linear discriminant analysis in Python. Linear discriminant analysis is a dimensionality reduction technique. If we have those data in 2 dimensions, and we know we have 3 groups, this group green, group blue, and group orange. We want to reduce dimension from 2 dimensions to 1 dimension. So what can we do? So if we project all those data to this direction, you can see we can separate the green dots, blue dots, and orange dots nicely. So this direction is the best projection direction. But if we project all those data to this direction, you can see we mix all the data together, so it's hard to separate them. So this is worst projection, this is the best projection. Regarding this dimensionality reduction, there is another technique called the principal component analysis, which I had another video before. If you are interested in principal component analysis, you can go to my channel to find it, or go to this URL to view my previous video. So what is the difference between principal component analysis and linear discriminant analysis? Imagine we have data here, and for the principal component analysis, we can use it when we really don't know how to group all those data. You can see in this graph, all the dots are blue dots, and we don't know which group they belong to. And in this case, we use PCA. So PCA is unsupervised machine learning method, and we'll consider all the data without considering the grouping. When we use this linear discriminant analysis, we know the grouping. So in this case, we know this group red and this group blue. So we are trying to separate all those different groups. So linear discriminant analysis is a supervised machine learning algorithm used for classification. So to summarize, PCA will find the projections that maximize the variance of the data regardless of their grouping. Sometimes because we don't know the grouping, so we have to use PCA. Well, LDA will try and maximize the distance between those groups. In this case, we use LDA because we know the grouping. In order to separate the original data according to their groupings, we need to transform the original data. For example, if we have the original X, and if we times transformation matrix A, it will give us a new set of data. If this new set of data equal to lambda times the original X, and this number lambda is the eigenvalue of A. And in this graph, you can see we are transforming those original dots. And after the transformation, all those blue arrows, they remain in the same direction, but only change the size. So all those blue lines are eigenvectors. And if we stretch them 2 times, 2 will be their eigenvalue. For the detail about the eigenvalue and the eigenvectors, you can go to the Wikipedia page to view the details. Now, let's go through the steps we need to perform for linear discriminant analysis. First, we need to compute the within class and between class scatter matrices. And then we need to compute the eigenvectors and the corresponding eigenvalues for the transformation. And then we can sort the eigenvalues and select the top k. If the eigenvalue is large, it means it carries most important information about the distribution of the data. Step 4, we will create a new matrix containing eigenvectors that map to the top k eigenvalues. And then we will perform the calculation to do the transformation. Now, let's take a look how do we implement that in Python. I loaded some wine-related data into Python. You can see in my data, I have group, and I have other like alcohol, malic acid, ash, all those characters of the wine. Let's take a look at my raw data. You can see this is a group, and then second one is the alcohol, and I have group 1, group 2, and group 3. I have 3 groups altogether. I have all 178 records for my data. And you can see the data is loaded here. I only show the first 15 records here. Then I will calculate the scatter within matrices. It shows this data. And next one, you can imagine, I'm going to calculate scatter between the matrices, like this. Next one, according to our steps, I calculated eigenvalue for all those characteristics of the wine. You can see the first 2 is very large comparing with the other characteristics. This is 15, first one. The second one is 5. Another one is all like power of the negative 15 or below. But this one is not very straightforward for understanding how much we can explain our data. Now, let's calculate how much we can explain our data. You can see the first eigenvector can explain about 73.6%, and the second eigenvector can explain about 26.4%. Altogether, it's about like 99.99% of our data. For the other eigenvectors, it's very tiny. We can basically ignore them. Then we perform the transformation. After the transformation, now we have the two-dimension data. Before the transformation, it's impossible for us to display. But now we only have two-dimension data. We can display them. You can see the three groups. The group 1 is gathered here, and this is average, and this is group 3 gathered here, and in the middle is the average, and this is group 2, and in the middle this cross mark is the average. You can see we separate them nicely after the transformation. If we draw a background, you can see we can separate them in this three area. This area is group 1, this area is group 2, this area is group 3. This is how I perform linear discriminant analysis in Python. Please provide your comments and subscribe to my channel. Thank you very much for watching.